Welcome to lecture 3 of module 3 on heat transfer.
In last couple of lectures, we have discussed on unsteady state conduction heat transfer, and this class also will be discussing on unsteady state conduction heat transfer. We have seen in case of unsteady state conduction heat transfer in previous lectures that how a lump parameter model is being considered, and then also we have seen that how a distributed parameter model is considered, and also we have seen the solution of lump parameter model, and then we have also seen some analytical solution of distributed parameter model for a semi-infinite body. Today also we will be looking into distributed parameter model and analytical solution for a typical type of conduction problem, and here we will be concentrating on infinite body that is subject of a definite thickness that is subjected to a convective environment which may be a cooling or heating. So, for the time being we will take care of a particular case, that is that infinite body subjected to sudden convective environment for cooling. So, this is a case when an infinite body can be considered a flat plate, it can be considered a long cylinder, or also it can be considered a sphere case. We will start with an example for a plain wall, and then we will see that how the analytical solution proceeds for this kind of situations, and we will see that the getting analytical solution to real life situations becoming complicated, and therefore, in future maybe in the next class, next lecture, we will be discussing how to get the graphical solution or with the help of existing figures or charts, how to get the solution for this kind of problems. Anyway, so let us concentrate on an infinite body subjected to sudden convective environment for cooling. Let us draw one picture. Say this is an infinite body, okay, and it is having a thickness, say a thickness is equal to say L. This x equal to 0, this x equal to L, and this x direction. So, this is the infinite body. Here that it is the length or the thickness of this infinite body is say L, and it is in the heat transfer we are concentrating on one dimensional heat transfer, and the heat transfer will be along x direction. The temperature initially, the conditions of this body is like this, that initially its temperature like T at x, any x for time equal to 0, that is the initial temperature will be T I, and then it is suddenly placed in a temperature when the surface is at a temperature of T s. So, cooling environment. At temperature T s. So, the body, the surfaces are placed at in a cooling environment when the temperature is T s. So, that surface is maintained at a constant temperature T s. So, this is the condition. Initially, it is at T I, and then the surface is maintained at a constant temperature T s, which is a lower temperature than Ti. That means, Ts is lower than Ti. So, heat transfer will take place from the solid wall to the environment because of the driving force of heat transfer. And this is a conduction phenomena. We are not considering the convection here because the surface temperature has been assumed to be a constant temperature case. Okay. Now, according to this, then T at x equal to 0 and for any time t should be equal to Ts. So, T x equal to 0 means the other phase, the which is that back side, that phase, the temperature of that surface is equal to Ts, and T at x is equal to L, and for any time t is equal to again Ts. Okay. So, this is the surface of this surface, the temperature is Ts. So, as I was telling, in terms of the reduced temperature, if you try to see, then T bar is the reduced temperature, and this is equal to T minus Ts. Ts is the reference because it is the temperature of the surface, and Ti bar is equal to Ti minus Ts. So, this is the reduced initial temperature. Okay. Now, this is the condition. Now, if we have to go for the analytical solution for this, we have to first start with the general conduction equation. In between, let us understand one thing, that it is an infinite body. So, there is no possibility of having any application of the lumped capacity or lumped parameter model, because it is a large body and there would be a variation in temperature and expected to be there in the slab. So, considering that situation, that there will be some variation in temperature with time as well as with coordinate. So, it is a distributed parameter system. We will take up the general conduction equation, and general conduction equation says, as we have seen already, for Cartesian coordinate system, or in general it is like 1 by alpha del T by del T is equal to grad square T plus Q dot generation by K, and we will assume that there is no heat generation. Okay. Then what is happening, that our equation is reduced to this form, grad square T is equal to 1 by alpha grad T del T by del T, and then we know that in case of Cartesian coordinate system, because we are concentrating on Cartesian coordinate, in case of Cartesian coordinate system, we know that del square T by del x square plus del square T by del y square plus del square T by del z square, and that is equal to 1 by alpha del T by del small t, that is the time. We know that this is a one dimensional heat transfer. We are considering, we are not considering for multi dimensions, we are considering only one dimensional heat transfer, and therefore, this there is no variation along x along y and z direction. Temperature variation along y and z direction is not there. So, this equation is further reduced to this condition, that del 2 t by del x 2 will be equal to 1 by alpha del t by del t. We have already seen that equation can be reduced to this form for one dimensional unsteady state heat conduction without heat generation. This becomes the equation. Okay. Now, we have to do this or solve this problem with the help of some analytical method. In the last class, we have discussed, we have demonstrated the analytical method where combination of variables has been taken into consideration. That means, combination of independent variables have been taken and a new independent variable was generated, and we have seen that say two independent variables. In the last class, we have seen two independent variables, that is the coordinate x and the time variable. They are combined to give a new variable which is eta, and then we solve that problem. Now, here what we will try to do is, we will be using separation of variables method. So, that is another method to go for analytical solution for this kind of partial differential equation. We can understand here there is a partial differential equation, and here x and t, these are two independent variables, and it is a partial differential equation because temperature is function of more than one independent variables, and therefore it is a partial differential equation. And this equation we will try to see that how it can be solved using separation of variables method. So, separation of variables method, that is what we are going to discuss for the solution. Okay. Now, to do this, what we have to first do is that we will be reducing these equation into dimensionless form. So, to have the dimensionless form of the equation, we know the equation is like this: 1 by alpha del t by del t is equal to del square t by del x square. This is the partial differential equation, and if I have to make it a dimensionless form, then I have to divide them, or in such a way I have to adjust that it will become a dimensionless form. For making an equation a dimensionless, we have to take up some non-dimensionalization scheme, that is called non-dimensionalization scheme. With the help of certain scheme, we can make that equations dimensionless. And so, if we say that y is equal to, this is t bar by T I bar, we have already seen what is T bar. T bar is the reduced temperature at any location, is equal to T minus Ts. Ts is the surface temperature when it is exposed to cooling environment, and Ti bar is equal to Ti minus Ts, where Ti is the initial temperature of the solid body of concern. Okay. And then we have that x will be dimensionalizing as x bar, and x bar is equal to, we will take x by L, L is the total length along x direction. Okay. So, another scheme that is for dimensional is the another variable, that is the t, time. Time is to be non-dimensionalized, and for that we will take up a variable, that is tau, and the tau will be writing as alpha into t by L square, and we know that it is like a Fourier number, and we know that alpha t by L square is nothing but the Fourier number. Actually, alpha is the thermal diffusivity, and L we have seen that is the total thickness of the slab that is being considered, and t is the time. Okay. Now, once we have these dimensionless variables with us at hand, now if we do the non-dimensionalization of the things, what we will get is that we can write the equation. If I say that it is equation 1, we rewrite equation 1 like this, as 1 by alpha del t bar by del t is equal to del square t bar by del x square. How? Because we know that 1 by alpha, we know that t bar is equal to t minus Ts. So, del t bar will be equal to del t, and del t bar by, sorry, if we write even more directly, that del t bar by del t is equal to del t by del t. Similarly, we can write del t bar by del x is equal to del t by del x, or del square t bar by del x 2 will be equal to del square t by del x 2. So, like that way we can reduce this, and then again if we put the expressions for t and x over here, so then what we get is, put the values of t is equal to tau L square by alpha. So, this 1 by alpha into del t bar by del of tau into L square by alpha, and then this will be equal to del square t bar by, we can have del x square, that is we can write del of x bar square into L square, like this. So, this thing will be many things will be cancelling with each other, and then we can finally write as that del t bar by del t is equal del tau will be equal to del square t bar by del x bar square, and also this can be written as del y by del tau is equal to del square y by del x bar square. So, this we can write because we know that y is equal to t bar by t I bar. This t I bar is a constant quantity. Okay, it is not a variable with respect to tau or x bar. So, this way the basic equation is now getting reduced to this form, and then what we will write is for this kind of solution, and then we will be getting our the boundary conditions and initial conditions to be reduced accordingly. So, if we write the initial condition now is changing to that we had initially that t equal to 0, we had t is equal to we had t I, and now we have tau equals to 0, then we will have y is equal to t bar by t I bar, and this is nothing but t I bar by t I bar, and this is equal to 1. That is the initial condition, and the boundary conditions for these cases are if we say that B C 1 boundary condition 1, initially the boundary condition was like this, that x bar equals to 0, we had t had been equal to T s for all time. Okay. Now, it is becoming now x bar equals to 0 for all tau, then y will be equal to 0. And the boundary condition 2 says in the similar fashion, boundary condition 2 says that x is equal to L, initially it was there for all t, t was equal to T s, and now it is x bar equal to 1 for all t, now here it is tau, y will be equal to 0. So, this is the boundary conditions. Okay. Now, if we have to apply these boundary conditions here for the solution. Now, before we apply the boundary conditions, according to the separation of variables method, we will assume a solution of this kind, that y as a function is a product of two solutions p x and q tau. That means, these are the separation of variables, that y is a function of a variable, or y is a product of two functions p and q. P is a function which is solely dependent on x, and q is a function which is solely dependent on tau. P is independent of tau or time, and q is independent of x or that coordinate. It should be x bar. Okay. From this, what we can do is that del y by del tau can be written as del p into q by del tau, and that is equal to del square p q by del x bar square. And what does it say? It implies del p by del thing, it implies that because p is independent of time domain, time variable. So, we can write del q by del tau, okay, and that is equal to q is independent of x coordinate or coordinate. So, we will write q here, we will get del square p by del x bar square. So, now what we can write is that 1 by q del q by del tau is equal to 1 by p del square q p by del x bar square. This is a very standard form, and this will be assumed as minus lambda square, where lambda is called it's a constant, and it is deliberately chosen as a negative quantity to have non-trivial eigenfunctions for p. Okay. So, lambda is taken as a negative quantity in a deliberate manner to have non-trivial eigenfunctions for p. So, now if we go ahead, then we can say that 1 by q into del q by del tau. Okay. This is equal to minus lambda square. Okay. And from here we can write that q is equal to, for this case the solution of this is equal to a e to the power minus lambda square tau, where a is a constant, integration constant. Okay. So, this one we can get, and here the initial conditions we know that tau equals to 0, y equals to 1 for all x bar. Now, if we go for the other part, that is that d 2 p by d x bar 2 plus lambda square p equal to 0. In fact, if we see the previously also, this expression we can write as 1 by q dq by d tau is equal to minus lambda square. So, we can make we can reduce this equation of partial differential form to the linear ordinary differential form. The reason is that q is a function of only tau. Similarly, here also we are writing the partial differential equation into an ordinary differential equation, and the reason is that p is a function of only x. Okay. Then if we see this, that the solution of this equation, many of us know that p equals to C1 cos lambda into x bar plus C2 sin lambda of x bar. So, this is the general solution for this equation that we know, and the boundary conditions for these cases also we have already seen that for x bar equal to 0 or y equals to 0 for any tau, and x bar equal to 1, y is equal to again 0 for any tau. So, these are the boundary conditions. Okay. Now, once we have seen that the two part, we have seen that there are two parts of this equation we have taken. So, the general solution of the equation is overall solution, overall general solution is y equals to C1 cos lambda x bar plus C2 sin lambda x bar e to the power minus lambda square tau. Okay. This is because that y is a function of y, and that is equal to p into x bar into q into tau. That is the solution we have assumed, and p is, we have found it like this into q already we have seen in the last these things is equal to this, and this the solution, that constant has been taken here, that is being taken care of by these two. Okay. Now, if we use the boundary conditions for getting the if we apply the boundary condition in this point, applying boundary conditions in this equation. So, what we can write at that for first boundary, from boundary condition 1, we can write that 0 is equal to C1 okay, and from plus 0, this implies C 1 equal to 0, and from boundary condition 2 we have 0 again will be equal to C 1 for boundary condition 2 x bar equal to 1, C 1 plus C 1 is part is equal to 0 plus, so this part is 0, C 1 is already 0. So, we have got 0 plus C 2 sin lambda x. Now, if we see that if we put that x bar equal to 1 here, then this part vanishes, this part goes 0, then C 2, this part is 0, then C 2 is equal to 0. It implies that C 2 is equal to 0, and if C 2 is equal to 0 and C 1 equal to 0, that is it is a meaningless solution for that. So, therefore, what is happening, we cannot say that this part C 2 equal to 0. If C 2 is not equal to 0, under that situation this is valid only when sin lambda x bar, or here actually x bar is equal to 1. I will just once we can further redo the things, that for boundary condition 2, 0 is equal to 0 plus C 2 sin lambda, because x bar is equal to 1, and that is equal to, that implies that C 2 sin lambda equal to 0. Now, the question is that either C 2 can be 0 or sin lambda can be 0, but C 2 cannot be made 0 or cannot be 0. If C 2 becomes 0, then total thing becomes meaningless. So, C 2 cannot be 0. So, only possibility is that sin lambda equals to 0, and sin lambda is equal to 0. We know that there is a there are for various values of lambda, the sin lambda can be 0, and therefore, we will write that eigenvalues, that is why it is called eigenvalues, many values of lambda can exist. So, eigenvalues is sin n lambda n will be equal to n pi, where n is equal to 1, 2, 3 and so on. Now, once we got the expression for lambda, then the general solution becomes y. We have then summation of n is equal to 1 to infinity. We have some b n is the constant, sin n pi x bar exponential minus n square pi square tau. Okay. Now, how this is coming? This is coming from this equation. Now, here if we see that this part is 0, y is equal to C 1 cos lambda x bar, and this C 1 is 0, this part is 0. So, now only this part is existing, and here we know what is lambda. Okay. Now, what we have to find out, actually this solution before we write, we have seen that C 2 cannot be 0, and we have found out what would be the lambda values, and then C 2 for different values of lambda there will be C 2. So, all these values are summed up in the form to give an expression like this, that summation of n is equal to, for all values of lambda, n equal to 1 to infinity, b n sin n pi x, okay, x bar rather, exponential minus n square pi square into tau. That becomes the general solution, and b n are constants. B n is equal to 1 to infinity. The are constants to be determined from initial condition. Sorry. Now, if we see the initial condition, IC, already we have seen that IC says that tau equal to 0, y equals to 1 for all x. What does it mean? That if we apply it over here, that 1 is equal to summation of n is equal to 1 to infinity Bn, okay, and then for all x bar here. So, for all x bar tau equal to 0, that means this part goes equal to 1. So, Bn sin n pi x bar, because the exponential part is becoming equal to 1 because it is tau equal to 0. So, now we have the expression that 1 equal to this. So, from this we can find out the values of Bn from orthogonality property of sine functions. Orthogonality property of sine functions. Using this orthogonality property, we can find out the values of Bn here. Now, how to do that and what is this orthogonal property? Orthogonality property says that a sequence of functions I will suggest that reader can go or go through any numerical method books or any advanced engineering mathematics book. You will find what is this orthogonality function and all. But however, just to have an idea about this, a sequence of functions phi I x, where I is equal to 1, 2, 3, etc., defined in an interval P and Q is said to be said to form an orthogonal set if integral within this domain P to Q phi m x phi n x dx equal to 0 when m is not equal to n, and integral P to Q phi m x phi n x dx equal to is not equal to 0 when m equal to n. So, when m equal to n, they are not equal to 0, and otherwise their products are 0. So, these two functions, this kind of functions are forming the orthogonal sets. So, this will be exploiting this behavior, this philosophy or this property of sine functions to find out the values of Bn. So, then what we will do is, if we multiply both sides of this equation, both sides of this equation will be multiplied by sin m pi x dx. So, multiplying both sides of the previous equation by sine another sine function, that is sin m pi x bar dx bar, and then integrating from 0 to 1, because we know that the span of x bar is between 0 to 1. X bar is a dimensionless quantity. So, its value varies from 0 to 1, and therefore, we will do the integration from 0 to 1, and therefore, we will get the 0 to 1 sin m pi x bar dx bar equals to 0 to 1. We had this expression n is equal to 1 to infinity b n, already we had this expression sin n pi x bar, and now we are multiplying with it sin m pi x bar, and we are multiplying with dx bar. So, then all terms of this right hand side, all terms will vanish according to the orthogonal property, except the term when m is equal to n. So, therefore, we can write, so using orthogonality property, we can write now integral 0 to 1 sin m pi x bar into dx bar, okay, and this is equal to b sum m and 0 to 1 sin square again m pi x bar. So, for n is equal to m, the value is not vanishing, otherwise the values are vanishing. So, we will write like this way dx bar. So, then we can write that integral of this is minus cos of m pi x bar, and this divided by m pi, and this is integrated between 0 to 1 will be equal to b m. Then we will write it 0 to 1, we will break it of this form, half into 1 minus cos of 2 m pi into x bar, 2 m pi into x bar, okay, into dx bar. So, now this is equal to b m, and then the integral of this is b m by 2 if I write into x bar, and then minus sin twice m pi x bar by twice m pi, and this is 0 to 1. Okay. So, then we get an expression that b in the left hand side will be equal to, we can write then b m by 2 will be equal to 1 by m pi into 1 minus 1 to the power m. We can see the left hand side for the different values of x bar, it can have a different, depending on the point your values of m, it can take up different values. That is what has been taken, that it can be plus 1 or minus 1, which is being reflected here. This is the expression for the left hand side, and this is the expression for the right hand side. Okay. And then if m is equal to even, we get right hand side equals to 0 and b m is equal to 0. If m is odd, right hand side is equal to 2 by m pi and b m is equal to 4 by m pi. Okay. So, what we will do is we will write that m equals to as odd, because otherwise the coefficient becomes 0. So, it becomes then again meaningless. So, for m is equal to odd, we will write it as 2 r plus 1, where r is equal to 0, 0, 1, 2 and so on. So, we can write that b 2 r plus 1, okay, that is equal to nothing but b m, and that is 4 by pi into 2 r plus 1, where r is equal to 0, 1, 2 and so on. Then we will replace that b 2 r plus 1 as in place of b n. Originally our idea to find out that value of b n. So, we have got that b n in terms of b 2 r plus 1, and then we will get the solution to be like this, that y equals to 4 by pi summation, say p equals to 1, I am sorry, r is equal to 1 to infinity, we can have sin 2r plus 1 by 2r plus 1, we should write sin 2r plus 1 into pi x bar by 2r plus 1 exponential minus 2r plus 1 whole square into pi square into tau. Okay. N is replaced by 2r plus 1 here, and then we can write this as further it can be written as is equal to y equals to T naught bar by T I bar, I am sorry, T bar by T I bar, and that is equal to T minus T s by T I minus T s, and which is equal to 4 by pi, and r equal to, we should write r equal to 0, r equal to 0 to infinity sin 2r plus 1 into pi x by L, where x bar is equal to x by L by 2r plus 1, and then exponential, if we write like this, minus 2r plus 1 whole square into pi square alpha t by L square this. So, this is becoming the solution, this is becoming the solution for the situation. Now, we can try to realize that how complicated it is to get a solution, and therefore, in general that analytical methods are not being practiced. It is being used, actually the solution whatever is obtained by analysis or analytical method, this is being used to generate different already some generate some figures or generate some charts for these cases, different cases, and then using the chart one can find out the value of different temperatures at different locations. Now, interestingly, this is the solution when we have considered the surface to be at a constant temperature T s. But in practice, it will be found out that, or it can be seen that that surface temperature is never a constant. Surface temperature is never a constant quantity. It happens to be a variable quantity. Like if we have, as we have drawn the case, this case, and this is what we have written 0 to L, x is equal to 0 to x is equal to L in this case, and this is the x direction. And we have initially we have thought of that this is a surface temperature, that is a constant temperature of the surface. But actually what is happening, if we see that there is a bulk here, then bulk temperature can be constant, and there is a resistance between the surface to the bulk. There is a resistance, and this is the surface temperature T s, and there is a bulk temperature. So, this bulk temperature or the temperature of the external world is fixed, whereas the temperature of the surface, okay, that may not be fixed. So, that is a, but the heat transfer coefficient which could be assumed to be constant. That means that the whole body is placed in a convective environment. Convective environment, and what is happening, because of convective environment, heat is being transferred the surface to this place, and it remains the driving force is continuously changing, and because the constant driving force continuously changing and heat transfer coefficient is assumed to be constant, then under that situation the heat flux is varying. So, it is a varying heat flux condition. So, as I told you that there are possibilities of several boundary conditions in case of convective heat transfer, conduction and convective heat transfer, or heat transfer from a solid body to the environment. there are different possibilities. One possibility, as we have discussed, that is the constant surface temperature. So, this is supposed to be a known value, and this constant surface temperature means there can be a resistance between the surface and the environment, but that is of not concern, that is not being taken care of while doing the analysis. And maybe sometimes it is assumed that the temperature of the fluid of the environment is having same temperature of the surface, that is why it is called constant temperature sometimes. Now, other than this, that another point is the constant heat flux, okay, at surface. So, constant heat flux means somehow, as because we know that from here to environment there will be a resistance, and because that surface temperature, if the heat is transferred from hot surface to the cold surface, the surface temperature of the cold body, cold surface, because of that, because the driving force will gradually decrease from the hot central line of the hot body to this. So, there will be again a difference in there can be a difference in heat flux. There can be a difference in heat flux with time, but what happens is as because that either you maintain the surface temperature constant, or otherwise the surface temperature will go on changing, and because surface temperature goes on changing, but T b is equal to constant, the bulk temperature. So, there can be a condition when the constant heat flux condition is difficult to maintain, but what is happening is that if you apply some external way of putting some energy by some external means, in that case the heat flux from here to here, either from this side or from this side, depending upon the situation, heating or cooling conditions. If it is a cooling condition, heat flux will be from here to here. If it is a heating condition, heat flux will be from here to here. So, heat flux conditions can be made constant with the help of some external supply of heat, or externally taking away some amount of heat, extracting some amount of heat. That is the second case, constant heat flux at surface. And third case, which is more practical, that variable heat flux at surface. So, variable heat flux at the surface, that is a more common case, and that is being observed. And for this kind of situation, we can understand for simple taking that T surface temperature, constant surface temperature, we have come down to such an expression, which is a very complicated expression. So, when you will take the variable heat flux, what does it mean? That at the two surfaces, variable heat flux means that at x equal to 0 or x is equal to L, heat transferred by conduction, okay, is equal to heat transferred by convection from surface to the environment. Sorry. So, typically, for example, if we say that one condition can be minus k into del t by del x 0 t equals to h into say T b minus t. So, if it is the at x equal to 0, this is the condition, and at x equal to L the condition is minus k into del t by del x at L t will be equal to h into t minus T b. It appears that, so there are two boundary conditions for the two surfaces. So, it appears, apparently it looks that heat is transferred from this surface and is going to this surface, but actually what is happening, it is transferred in both the surfaces, and this is a cooling environment. So, what is happening for this surface, it is a positive x, for this surface it is a negative x. So, that negative part del T by del x and minus takes care of in this equation, it is being taken care of, and then it will become H into T minus T b, and heat will be transferred from this side to this, and in this case heat will be transferred from this side to this. But anyway, this is a general form of the cases when heat is being transferred from one surface to the other, or and from one phase to the other with the help of this mechanism, conduction and combination of conduction and convection mechanism. Okay. So, this is becoming the boundary conditions. Initial conditions remains the same. The boundary conditions is complicated, and using these boundary conditions we have to develop, or one can develop the analytical solutions available. These analytical solutions are available not only for this kind of boundary conditions, analytical solutions are also available for infinite cylinders and for spheres. What is mean by infinite cylinder? A cylinder, a very long cylinder, infinite cylinder means is a very long cylinder, but of a definite diameter or radius. Okay. This is the center line temperature. So, definite diameter or radius. Then also it is possible for a sphere of a definite diameter or radius. Okay. Now, under these cases, for long cylinders or infinitely long cylinders or the spheres also, or the analytical solutions are possible, but in practice it is becoming difficult and complicated things, and for particularly for undergraduate students, for higher studies and for doing some research and research oriented things, that the solution of these equations may be of useful, and the students, interested students, may really go into some references and find out how to solve this. But as a means of this undergraduate curriculum, I think we should not discuss further details or further complicated cases in analytical method of solution of conduction heat transfer problems. So, in the next lecture, what we will do is we will try to make use of charts, available charts and existing charts, for finding out the temperatures at different locations, as well as heat flow for such an infinite bodies, and how it happens, and how the charts or the existing figures are being taken into consideration to calculate these different or to get the informations about temperature and the heat flow conditions. Okay. So, in the next class we will discuss about application of various charts for calculating the heat flow conditions. Okay. Thank you very much.